Welcome to a quick run through of some notes to just kind of consolidate what we've learned about inclined planes. We are assuming that you have already done the lab. So we're going to be on workbook page 137, and at the top of 137 we have a simple situation where we have an object that's sitting on a flat surface and no other forces are involved. So we have gravity pulls down and normal force is pushing up, and since this object is standing still, we know the acceleration is 0, so these two forces have to equal each other. Again, only two forces. Forces must be balanced. Well then, normal force equals gravity. Okay, but if we take that surface and start tilting it, in the first situation, normal force was equal to 100% of gravity. But as we tilt it, if there's no friction, this object is going to start sliding down. Normal force is not going to be canceling out gravity anymore. And in fact, normal force is going to end up being a little less than gravity. And this will be apparent on why it has to be. As we tilt it more and more, it's being pulled into the surface less and less. So with less and less force into the surface won't push back as hard. So normal force gets smaller and smaller until, if it's a vertical surface, and there's nothing actually pushing the object in, our normal force will equal 0. So at this point, we've gone from 100% of gravity down to 0% of gravity. And if that's our case, if normal force is not canceling gravity, it's not canceling gravity at all, but even if it's only partially canceling gravity, in these other cases, in all of those cases, the block would accelerate. It would accelerate down the ramp, parallel to the surface. So as our percentage of force of normal force goes down for canceling gravity, our force parallel to the ramp increases. This is our accelerating force. So if we take this and break out and look at our situation a little bit differently, we have a tilted surface. Gravity is still pulling down. And we know that normal force is going to push out, but normal literally means perpendicular to the surface. So it's out, perpendicular, away from our surface. And we're going to tilt our perspective so that our x and y axes, instead of being horizontal and vertical, they are parallel to the surface. X is parallel, y is perpendicular. And that means, from this perspective, normal force is all y, but gravity has an x and a y component. Normal force is not equal to gravity here, neither in direction nor even in magnitude. So what we get is a force of gravity into the ramp, perpendicular to the ramp, and a force of gravity down the ramp, parallel to the ramp. So these are components. If you tilt your head so that the ramp is flat, seems flat, normal force seems straight up, gravity seems, our parallel force seems directly to the left, and our perpendicular force seems straight down. The original gravity force is diagonal in this, and so we're splitting it into components. So in this setup, normal force is going to equal the force into the ramp, the force perpendicular to the ramp. And our force down the ramp, that would be accelerating in this case, is the FG parallel. Now, in our lab, we figured out that if you tilt by an angle theta, that your FG parallel is going to equal our original force of gravity times the sine of theta. On this triangle that we can see here, FG parallel is across from theta. It's opposite. So that component is found using sine. FG perpendicular is going to go with cosine of theta. It is adjacent to the angle theta. Now, when it comes to problem solving, trying to derive this every time is a pain in the butt. So we don't usually tell you you should just memorize a formula, but this one, worth memorizing. Force down the ramp is force of gravity, mg sine theta. Force into the ramp is mg cosine theta. And so you can practice with these problems on page 159 on the right-hand side. And in another video, I will tackle one of the typical problems, and of course the solutions are available as always. Thanks for watching, and happy physicsing.